Hello folks, we're back with more integrals. Today we're going to do triple integrals. Now, the way we're going to set up and apply triple integral is going to be kind of like what we did for double integrals. If you remember, we could use the double integral to calculate the volume under a surface, under a three-dimensional surface, or we could just simply use it again to find the area of a region in the xy plane, just good old two-dimensional. So you with the double integral you can do three-dimensional stuff like volume, and you could also just use it to calculate areas as well. So the same thing is going to apply for triple integrals. We can have triple integrals calculating volumes, or we can have triple integrals calculating functions over three-dimensional solids. Okay, so double integrals calculated functions over two-dimensional regions. Triple integrals are going to calculate um, are going to help us to deal with functions over three-dimensional solids. Okay, so let's say let's say we wanna we want to find the mass of some object, okay, some solid, and we know its density at any given point. Okay, so we have some three-dimensional object, okay, and there's a function that assigns a density value to each given point on that object. Okay, so if we think about that function as, let's say, delta xyz, d for delta xyz, and um, this delta is continuous. To calculate, once we know density at each point, to calculate the mass, we would have to integrate this density over the whole solid. Okay, so we'll have the triple integral over the whole solid of this function, continuous function. We said in our example it was a density function, dv, just like the double integral was over the region, okay, over the region, dA, this is dv, where this is the volume differential. Okay, now to calculate this integral, okay, it's fine writing it down, but how are we going to calculate it, and how is it defined? What does it mean to do a triple integral over a three-dimensional solid? What is this dv? Um, Now, to do the setup, we're going to do the exact same thing we did for double integrals. For double integrals, we divided the region into rectangles. For triple integrals, we're going to have a solid, something like this, inside my hand, and we're going to divide it into little boxes, rectangular boxes, three-dimensional rectangular boxes. The width of each box is going to be delta y, delta x, delta z, where I put sub k to show that this is the kth box. Now, in general, the boxes don't have to have the same volume, don't have to have the same dimension, but we're going to assume here that they are going to have the same dimension. That's easier to handle, okay? Um, and in that case, if I'm trying to calculate just the volume of this region, um, and the function is defined over the volume of this region, what we need to do is we need to do the Riemann integral, okay? F of xk star yk star zk star. F is a continuous function. It's got three independent variables, so this guy is four dimensional, right? It's assigning, given any three points in the tree space, it's assigning a value like its density, okay, um, to each of those points. The reason I put star is these are any points, xk, yk, zk star are any points in the kth box, okay, however you divide it up. Delta vk, and delta vk is just going to be the volume of the kth box, so delta vk is actually going to be equal to delta zk, delta yk, delta xk multiplied together. Okay, um, so this is the Riemann definition of it. Of course, in the Riemann definition, you do not need to have the boxes to be or the boxes to have the same dimension. They could have different dimensions. We can think about a partition. The idea that p goes to 0 is saying that the volume of the largest box goes to 0. In that case, again, you're going to end up with infinitely many boxes, so you're going to exactly approximate the volume of the region. Okay, So the idea here is if I don't do it, if I don't plug in a function in it, if I just do the integral dv right here, like here at the bottom, and I don't plug any function to it, we're just calculating what happens to the volumes of these boxes when I add them up. Well, when I add all those boxes up, I just get the volume of the three-dimensional solid. So volume is always equal to the triple integral dv. Okay? Mass, on the other hand, is going to be equal to the triple integral of the density function. Now, the density function is a three-variable function. Of course, it's got delta x, y, z. It assigns a density value to each one of these points. And we could do the centroid, the center of mass for engineers. So you're going to get the x coordinate of the center of the mass by saying taking the integral, triple integral of x times the density dv and dividing it by m. Okay, I'll talk about why we're doing this in a second. Similarly, you're going to get the y coordinates of the centroid by taking the triple integral of y times the density dv, and similarly you get dividing it by m again, and similarly you get the z coordinate of the centroid by taking the triple integral. This time you're multiplying delta by z dv 1 over and multiplying by 1 over m, or dividing by 1 by m. Okay, so where does this x times delta business come, or y times delta, z times delta? The reason you get x times delta is if you have the center of an object and you're d away from it, d distance away from it, the force that you feel downward, okay, if you apply any force or just the gravitational force, this point applies much more force. It's proportional to the distance from the center. So you have the density function, how heavy in some sense that point is, and its center, its x value, basically x coordinate, and that's the effect of that point to the whole overall center of mass. You could also calculate inertia like this for engineers. That you're going to find formulas for that in your calculus book. I'm not very interested in right now the physical applications. Let's get the theory out of the way. We've seen the Riemann integral. We still haven't seen how we're going to set these integrals up and calculate them. So I would like to do that next. See a couple of examples of actually doing these. Okay, so the idea is, again, just like I said a few seconds ago, how do we actually calculate these triple integrals? And now I drew a picture here. Oh, it's a horrible picture. We have a three-dimensional solid. Let's call this guy T, living in 3 space. And I drew its shadow. Or its projection on the xy plane on the bottom. Okay, so this R is the shadow of this if you were shining light up from above. Okay, and you would get this region R. So let's say it's like elliptical. Okay, so what we're going to do is we're going to kind of think that we're doing vertical elements. So for each 2 points here, we're going to do all of these lines over the whole 2-dimensional region R. Okay, so what we actually mean by the triple integral of the function f, again, you'd like f to be continuous, over this solid T, is you actually want to integrate just over this region R, the double integral, times the integral top minus bottom, z top minus z bottom. I said, though, let the top one be f2 and the bottom one be f1 of x, y, dz. So what you're doing is you're doing the z coordinates first. You can actually do any coordinate as long as it works out first, but usually these integrals are going to go dz, dy, dx. That's the easiest one to think of. Again, we're going to see examples in a second. dz, dy, dx. So you do the heights again, just like we did for double integrals. You do the heights, and in, out, okay? And you do that first integral, and then this triple integral basically reduces to a double integral, whatever the heck this is. Okay, it's gonna be a function over a region dA. So it's gonna reduce to a double integral, which we already know how to handle. Okay. So, okay, so again, this is lots of theory. Let's actually see this in action. And what we'll do is we're going to try to find the volume of of the solid bounded above by the paraboloid z equals 3x squared minus y 3 minus x squared minus y squared, and below by the paraboloid z equals 2x squared plus 2y squared. Again, I would suggest that if you're able to draw these, you should basically try to draw them to see what's going on. It's a lot easier to set up these integrals when you see the whole solid. So basically what's happening here is the paraboloid z equals 2x squared plus 2y squared is opening upwards. It's opening upwards. Think about my hand, and then it's got a circle in it. Okay, it's opening upwards, and the other one is opening downwards. Okay, so the two paraboloids are going to intersect in a circle. Okay, in a circle. So that's going to be basically this circle that I try to draw inside it. That's going to be our region R. So let's calculate what that is, where they intersect. So we set them equal to each other. 3 minus x squared plus y squared equals 2x squared plus 2y squared. And the math is simple. If you just do one step, you get that the circle of the formula is x squared plus y squared equals 1. In other words, it's the unit circle. Okay? So now, let's set up the triple integral. So the triple integral, to find the volume, we're going to do the triple integral of dv, and that's just going to be the double integral. Now let's think about the heights here. Let's think about the heights. The top is going to be 3 minus x squared plus y squared, and the bottom is going to be 2x squared plus 2y squared. So on the bottom we get 2x squared plus 2y squared, and on the top we get z equals 3 minus x squared plus y squared. We get dz, and then it's going to be the double integral over the region dA, where the region is of course the region of their intersection, and that's going to be the unit circle. Okay, so now I can try to do what I'll try to do is I'll try to now set up the rest of it. What's these two integrals? Well, we're trying to integrate over the region R, which was the unit circle. So I just drew the unit circle on the xy axis. Okay, xy. So again, because the formula is x squared plus y squared equals 1, that's going to imply that y squared is equal to 1 minus x squared, and y is plus or minus square root of 1 minus x squared. Okay, so the top square root is basically the top half of the circle. We've seen this before. And the bottom half is the negative square root. Okay, so now I'm going to do vertical elements again because that's easier to think of. Well, where do the vertical elements go? It goes from the top function, y equals 1 minus x squared, to the bottom function, minus 1 minus x squared in the square root. And we're going to scan this like this from left to right. Okay, so the x values are going to go from minus 1 to 1, and we already had our z values. So the first integral is dz, the second integral is dy, the third integral dx, and that's it. That's the volume basically. Now, all of these questions of course have two parts to them. The first part is setting up the integral, the double integral, the triple integral, whatever it is. And the second part is solving them, okay? So when you're trying to do these problems as homework problems or whatnot, you kind of, because they are kind of long, you have three integrals inside one question, people think it's really, really hard. It's not, okay? Just divide and conquer. It's two different things. Set up the integral, then solve the integral. What's really, really important at this stage, what's the more important thing is that you set up the integral correctly, okay? Solving it is just a Calc 1 question. So if you get stuck on trying to solving a integral, we're always doing these integrals at one step at a time. It's a Calc 1 question. You can go and review your Calc 1 integration techniques like by-parts or substitution or trigonometric substitution and all those other techniques that people see in a Calc 1 class. So don't get scared. The more important thing here is actually setting it up correctly. If you don't set up correctly, no matter how good you're at the integration, you're not going to get the correct answer, right? So let's concentrate on solving it. Then let's concentrate on setting it up. Then we're gonna look at solving it separately. Okay, so for this question, now let's actually try to do this integral so that you have a complete example in your hands. Okay, so once I integrate dz, of course, all I get is z. all I get is z. And so that was from the bottom function, which was 2x squared plus 2y squared, to the top function 3 minus x squared minus y squared. So plug those in, and you get this guy minus this guy is 3 minus 3x squared minus 3y squared, okay? Now, we're down to a double integral, and this comes back to last week's subject, which was substitution. You know, I could go ahead and do this. Um, it's not hard, right? It's going to be, if I do rectangular integrals, it's going to be 3y minus 3x squared y minus 3y cubed. But once I plug in these square roots, my integral is going to have a whole bunch of square roots in it, okay? A whole bunch of square roots in it, which I'd rather not do because you would need trigonometric substitution, or you could be a little smart and see them as the areas of circles, but it takes a longer time. So let's try to apply what we learned last time, and let's do polar substitution. Why do I suspect we might need to do polar substitution? Well, first of all, the region was over the unit circle, so that's certainly circular. And here, look at it. This is 3 minus 3 times x squared plus y squared, right? 3 minus 3 times x squared plus 3y squared. So that immediately says, it's shouting at me, hey, I am 3 minus 3r squared. So you're right. If the function looks nice when you look at it from polar coordinates as well. Okay. So now let's actually set up the region for our polar conversion. We always use x equals r cosine theta, y equals r sine theta, and r is between 0 and 1, and it takes 2 pi radians to go around the whole circle, basically, okay? So the integral part of it is simple. R equals 0 to r equals 1, and theta equals 0 to theta equals 2 pi, okay? Now, you could also use symmetry for this function because both the three-dimensional object and the region have circular symmetry, but I'm just gonna do it in one piece. We have this, and we have 3 minus 3r squared, that's our function. 3x squared, 3 minus 3x squared, 3 minus 3y squared is the same thing as 3 minus 3r squared. And remember, we did this last week. Because of the Jacobian, dy dx gets converted to dr d theta, but the Jacobian is r, so it comes down to r dr d theta. This is what happened when you did polar substitution every single time, okay? So now we have our integral. We just multiply by r, you get 3r minus 3r cubed. Integrated, you get 3r squared over 2 minus 3r to the 4 over 4 from 1 to 0. So that boils down to 3/4 theta from 0 to 2 pi. And that's 3/4 theta, evaluate from 0 to 2 pi, and you get good old 3/2 pi. Okay, so again, the setting up is something, the solving is something else. And we set it up while we're solving it just to do a review. Because this had a lot of circular symmetry, we did polar conversion here, polar variables, and the integral was much nicer. Otherwise, you do trigonometric substitution, basically. Okay, now let's do a more interesting question. Let's do a harder question. Find the volume of the solid formed when the elliptical cylinder x squared plus 4y squared equals 4 is cut above by z equals x plus 2 and below by the xy plane. So I tried to draw it here. I wasn't really successful. Basically, what you have is a cylinder, right? Cylinder is going on forever. It goes down forever. It goes up forever. And we're cutting it by z equals x plus 2. So we're basically cutting it by a plane. So this cylinder is going to get cut by a plane. And then we're going to try to calculate the volume there. Now, because my drawing here is horrible, you can't make sense of it at all, I gave up and I decided to just make the whole thing, okay? So here is what we made out of a roll of toilet paper. Basically, we have the cylinder. The toilet paper roll was going on, think about up and down infinitely, and the plane z equals x over 2 just cut the toilet paper roll like this, okay? And the bottom is elliptical. The bottom is an elliptical cylinder, so it looks like an object like this. Now I want to calculate this guy's volume, how much stuff is in here. Okay, again, let me show it to you here like this. It's elliptical on the bottom, and basically what it was we cut the cylinder with a plane. Okay, so all right. Having said that, let's talk about the region R. Now, if you look inside it, okay, the projection of the whole thing, region R, is just the elliptical region x squared plus 4y squared equals 4. Okay. Now, I don't like writing ellipses that way. Remember, the easier way to think of an ellipse was x over a squared plus y over b squared um, equals 1. So this is, I divided by 4, you get x squared plus 4 y squared equals 1. So when you think about this, the x-intercept of this ellipse is at 2. A squared is 4, so a is 2. And the y squared over 1, this y squared is 1, so the y-intercept is 1. Okay, it's a sideway ellipse. Okay, so that's the region. Now let's talk about our integral. So this triple integral over the region t, which is basically t is this guy, okay? dv is going to be the double integral over the region r. The region r is the ellipse. Now let's think about the heights of these, okay? So the top is going to be the plane, which was z equals x plus 2. So the top is z x plus 2. The bottom is the plane z equals 0. In other words, it's the xy plane. It's the good old xy plane. dz times dA, where r is the elliptical region again. So if we do that, we get over r, z, integral of dz is going to be z from z equals x plus z, from z equals 0 to x plus 2. And that's just, of course, x plus 2. So we have over the region of the ellipse, okay, just the function x plus 2. Okay, now that looks like an innocent integral. It really is not. Okay, it's going to be a little exciting. The issue here is, again, we have to now draw the region R, the ellipse x squared over 4 plus y squared equals 1. We have to draw that. So I did again. Let's say we're doing vertical elements. If you solve for y, you get y squared is equal to 1 minus x squared over 4. So y is equal to plus or minus the square root of 1 minus x squared over 4. The x squared over 4 is inside the over 4 is also inside the square root. Okay. So again, just like the circle, the top part is going to be the positive square root, and the bottom part is going to be the negative square root. Okay. So now, if leave the function alone, we don't have anything to do with that guy. The bottom is the negative square root. The top is the positive square root. Okay. And we're going again sideways with vertical elements, going like this. So x is going to change from minus 2 to 2. Okay. dy dx. Now again, of course, if we try to do this integral, it looks innocent enough. Again, we're going to get lots of square roots, okay? So just for a change, I decided, we've set it up, we've solved as far as we can right now. Now we have to deal with the rest of it. And the rest of it is either trigonometric substitution, or I'm going to show you a new substitution, elliptical substitution here actually. So I did both of them. The first way is we just go ahead and integrate it, and in which case this is going to, because this is x plus 2, this is going to be x plus 2 times y. Evaluate from this square root to this square root. Well, this guy minus this guy is going to make twice this guy, okay? So twice the square root basically. So we're going to end up, once we evaluate it, we're going to end up with x plus 2 times twice the square root inside the integral. Now, as you can see, that's not fun, right? Or it is, depends on how you look at it. That's going to be a trigonometric substitution, but I did this without using any trigonometric substitution, just to show you can do these really fast if you're on top of your Calc 1. So if you multiply through, so you get 2x times the square root and 4 times the square root. Break up the integral, okay? Now this is minus 2 to 2. If you notice, this function inside is an odd function. What was an odd function? It was symmetrical or around the origin. So if you do it from minus 2 to 2, this area is going to cancel out this area, and you're going to get a good old 0. Okay. If you do it from minus 5 to 5, again, any odd function from minus a to a, the integral is going to be 0. So I use that smart idea. Okay, kind of smart once you realize it. If you didn't realize it, you're going to do a trigonometric substitution. So this whole integral went to 0. Now the next one is actually what? This top one was basically the positive square root was the top half of the ellipse. So what this guy is saying is just to get the area of the ellipse, only the top half, and multiply it by 4. Again, you could do trigonometric substitution, or you could turn it into a geometry question, which this time, just to do something different, I turned it into a geometry question. So the idea is, well, how do we calculate the area of the top half of the ellipse? Okay, so if you have the formula memorized for the area of an ellipse, that's going to be easy. So remember, when you have a ellipse of the form x squared over a squared plus y squared over b squared equals 1, so basically ellipse that has that has that is either horizontal or vertical, and the x-intercept is a and the y-intercept is b, then the area is just pi times ab. Okay, one way to memorize this, if you can't keep it in your head for the life of you, is to realize that an ellipse, a circle, is a special case of an ellipse. So this would be a circle if this was x squared over r squared, y squared over r squared, because once I multiply by r squared, I'd get x squared plus y squared equals r squared. So in that case, of course, you'd like the area to be pi r squared, which is basically pi r times r. Okay, so that's where it comes from, pi ab. Some professors prove the ellipse of the area of an ellipse when they're teaching trigonometric substitution in Calc 1. I always do it because it's such a nice thing and it's got so many applications. So basically now we know we have to find the area of the top half of this ellipse. Well, the x-intercept is 2, the y-intercept is 2. So normally the area of this ellipse would be just 2 pi, okay? But we're just talking about the half the area, so it's going to be pi. And we had 4 of them, the 4 in the beginning, so basically it's going to be 4 pi. So that's one way to do it, using geometry and odd functions. You could also use trigonometric substitutions. That's one way to do it, okay? Another way to do it, which is kind of new, is we can try an elliptic substitution, okay? We haven't talked about that before. Let's try to do it. So again, we were trying to do this integral x plus 2 over the region, which was x squared over 4 plus y squared equals 1 over the ellipse. We were trying to do this. Now, because we're doing ellipse, okay, what we're going to do in general, when you have x squared over a squared, y squared over b squared equals 1, you can make this substitution ar cosine theta, x is equal to ar cosine theta, y equals br sine theta. Why? Because it works. I know it works. You can kind of get this from the polar parameterization of an ellipse, if you remember that from Calc 1. Okay, so in our specific case, a was equal to 2, b was equal to 1, so we have x is equal to 2r cosine theta, y equals r sine theta. And again, r is going to be between 0 and 1, and it takes 2 pi radians to go around the whole ellipse. For this one, now that we made the substitution, it's a little different than the polar substitution. We actually have to calculate this Jacobian. Remember, the Jacobian is going to be x sub r, x sub theta, y sub r, y sub theta. We're going to take the determinant of it, and then we're going to take the absolute value of the determinant and plug it into the integral. Okay, so derivative of x with respect to the radius, well, that's just a is a constant, b is a constant. So that's just going to be a cosine theta. In other words, for us, a was 2, so it's 2 cosine theta. And derivative of this with respect to theta is now going to be 2r sine theta. There's going to be a minus in front, so we put the minus sign, okay? And derivative of y with respect to r is going to be sine theta. And derivative of y with respect to theta is going to be r cosine theta, okay? So if you take the determinant, multiply this way, subtract this way, okay, you get 2r cosine squared plus 2r sine squared is equal to, well, what is that going to be? Sine squared plus cosine squared is 1, so it's just equal to 2r, okay? So that's my Jacobian, and we're assuming we're going to plug it into our integral. So this integral over the region r, over the ellipse of x plus 2 dA, becomes r equals 0 to r equals 1, and theta equals 0 from theta equals 0 to theta equals 2 pi. Now, x plus 2, what is x plus 2? Well, x was equal to 2r cosine theta. So x plus 2 is going to be 2r cosine theta plus 2. My Jacobian 2r dr d theta. This is my Jacobian 2r. Okay? So multiply through. Now this is an easy integral. Multiply through, you get 4r squared cosine theta, 4r dr d theta. So when you integrate it with respect to r, this is going to be 4r cubed over 3 cosine theta, and 4r squared over 2, which is basically 2r squared. Evaluate from 0 to 1, and you get 4 over 3 cosine theta plus 2, evaluate from 0 to 2 pi. So integrate that, you get 4 over 3 sine theta plus 2 theta from 0 to 2 pi, while sine at those points is 0, so you don't get anything from there. Plug in 2 pi into 2 theta, you get 4 pi, and minus 0 is 0. So we again get 4 pi, exactly the same answer. Okay, if we had gotten something else, we would know we messed up somewhere. Okay, so that's all I'm gonna do here. Again, we were talking about triple integrals. They are very similar to double integrals. Once you do z top minus z bottom, it just reduces into a double integral, which we already know of. And setting it up is something, solving it is something else. What I would suggest for you to study is just open up any calc book, look at the triple integral questions, and just set the integrals themselves up. Don't solve them. Just go around, maybe do 10 questions, 15 questions. Just set the integrals up. Don't worry about solving them, okay? Solving them is a Calc 1 question. Setting them up is a Calc 2 question, or Calc 3, depends on how you take your calculus, okay? So setting them up is the multivariable calculus question. Now, I'm going to end this here. Next time, we're going to talk about cylindrical and spherical coordinates and how we set up integrals using those coordinates. So they're going to be different than polar coordinates. And I hope to see you then. Take care. Bye-bye.